Our next speaker is Kamalika Chaudhuri, and she's going to talk about a specific differential privacy mechanism.
Thank you very much. So first of all, I'd like to thank the organizers for putting together this very nice workshop, with a great collection of people. And to keep in theme with the workshop, what I'm going to talk about is some work that we have been recently doing that combines insight from, all three, database, theoretical computer science, and machine learning communities. And, I would love to hear your thoughts on this. What I'm going to be talking about is not exactly differential privacy. It's about a slightly different class of privacy problems where differential privacy is not quite the right fit for these, right? And it'll become clear, why that happens in just a little bit. And I'll tell you about some work that we have been doing in that space over the last year or so. Okay, so as you know, Kunal helpfully introduced these problems for me. So we have a lot of sensitive data, and what we want to do is we want to make inferences based on these data sets, right? And we want to preserve the privacy of individuals in this data. So in this talk, what we are going to do is we are going to tackle the question of how do we analyze sensitive data while still preserving privacy. Okay, so this is kind of the theme of this talk, and our focus will be on correlated data. Right? So what do I mean by correlated data? Let me start with a couple of examples. So one example would be if you have a social network and you have information from people in the social network who are connected together and their attributes are very correlated. And I believe Lisa has done some privacy work in this particular context. So this would be, and she has shown that it's very hard to preserve, to stop an adversary from inferring stuff about you in this context, right? Another example would be physical activity monitoring. So here what is happening is you have a single user and you have a lot of information of what this user did across time, and now you would like to publish some sort of aggregate information, but you want to guarantee some measure of privacy, right? Like you can't hide everything about the user, but probably what you can try to hide is what the user was doing at a specific time point while publishing how much he walks in, let's say, a week. Right, so these kinds of.
What's correlated here? What's the correlation?
So the correlation here is that the activities are highly correlated across time. So what I'm doing right now is highly correlated with what I was doing 5 minutes later, right? So why is privacy hard for correlated data? So I will get into this in a little bit, but generally this is the one sentence to remember, right? So the one sentence to remember is, because neighbors, so if you have a bunch of variables that are correlated, if you infer something about one, then that will leak information about something about the other one, about the next one, so something that's correlated with you, right? So this is kind of the basic underlying reason, and now we will look into more specifics in a little bit, okay? So, how do we define privacy? We are going to talk about how to define privacy for correlated data. First, let's start out with privacy for uncorrelated data. Okay, and for uncorrelated data, so we are going to start out with differential privacy, and Kunal already defined this, but I want to highlight one specific aspect of the definition, and then we will see how when we are dealing with these kinds of applications I talked about, this specific aspect is doesn't quite hold, right? So here, remember in differential privacy, what we wanted to guarantee was that the participation of an individual does not change the outcome, right? So for example, if you have an adversary who has some prior knowledge and they use the output of the algorithm on some data, including Alice's data, to draw some conclusion about Alice, well, they could have done the same thing if Alice was not on this data set and Bob was in the data set instead. Okay, so this is differential privacy. And there are a couple of things to note. So one is that the algorithm could still draw a lot of personal conclusions about Alice, right? But the point here is that Alice is the person who has the agency to participate or not, right? Alice could say that, look, this algorithm, Alice could say that, look, this risk is too much for me. I decide not to participate in the database. And this is, completely Alice's decision, right? So this is Alice's agency. She can decide to participate in the database or not, okay? So one of the things to note here is, conclusions, harmful conclusions here are being drawn about Alice, and Alice has the agency to participate or not. Okay? Now, what happens with correlated data? So here is the activity monitoring example. Here our job is to share some aggregate data on the physical activity. And so this is in a slightly more limited setting. So I'm not hoping to put this up on the internet, but I'm hoping to, let's say, maybe show this to my doctor or nurses and so on. And what I want to do is I want to hide the activity at a specific time, right? Here, the agency is at the individual level. I have the agency to participate or not, right? It's not that what I do at time t has the agency to participate, right? So I have the agency whether I want this to happen. So this assumption that I don't want harmful conclusions to be drawn about Alice, and Alice has the agency to participate, that particular assumption doesn't really hold, right? That particular condition doesn't really hold. Okay, yes, question.
So when you talk about correlation, you mean an explicit correlation?
Yes, yes. So we'll come to that in just a little bit. Okay. So this is something that is going on here. Okay. Another example, which I won't go into in a lot of detail. So the first example actually, the physical activity monitoring example is kind of the one to keep in mind throughout this talk. And this example kind of arose when one of my colleagues who works on embedded systems, came to me and said, oh, look, we have all this data, and we kind of want to share them with researchers, and we don't know what to do. There's something, can you do something? And you say something about its privacy. So that's how I got interested in this problem. So here is another example, which is which we will also be able to say a little bit about, is let's say what you are doing is you have a set of schools, and the schools there's a survey, and the schools have the agency to participate in a survey which says and which is a survey about, let's say, how many people have flu in the school, right? And here what they would do at the end of the survey is publish aggregate statistics over a set of schools. But what you would like to do is to prevent an adversary from knowing who has flu, right? Here, the agency is at the school level, right? So the school makes a decision to participate or not, but the individual students in the school may feel like they don't want their privacy to be violated, right? So again, this unit of agency versus unit of information hiding is different here, right? So this is a slightly different setting, okay? So what happens when you use differential privacy for correlated data? So here are, so let's look at the activity monitoring example closely, right? So here our goal is to publish the activity histogram over a reasonably long period of time, right? Let's say maybe some weeks or something, right? And you want to prevent the adversary from knowing what the person was doing at each time t, okay? Here, remember, agency is at, the individual level, not at time entry level, okay? Okay, so what happens if you use pure differential privacy? What would happen is, notice this is one person's data, right? So pure differential privacy, you would just add enough noise to hide one person's data, and it's not going to be exactly the right thing to do, right? So there would be too much noise. Okay. Another option is, because you are just, there's just one person, and you are hoping to hide, all about one person, right? So, imagine one. So generally, I guess this is the kind of thing that Kunal was trying to get at is the reason. So what differential privacy is doing is, if you have aggregates over many people, then you blur the contribution of one person, and and that preserves the aggregate over many people, but not one person.
Here it seems that is the activity that you want to do.
Yeah.
Not the fact that
No, I know. I'm just going over some, yes, I agree with you. I'm going over some base cases. So let's wait till this is done. Okay?
Oh, I don't see I don't see the reasoning. Go back one side. I don't see, what's the reasoning for too much noise?
Oh, the too much noise is here. This is just one person's data, right? So you would add enough noise to mask a single person's data. So this is like getting differential privacy for one person.
It's like a data set with one element.
Yeah, exactly.
You want to make it indistinguishable from one with 0 people, so
yeah.
Clearly it can't have any.
It can't have any utility. Okay. So the next one would be entry differential privacy. So here you can say that the participation across, over entries of if the participation of a single entry will not make a difference, Here, what you would do is you would output a histogram of activities, and you would add noise with standard deviation 1, right? So this is, this is maybe a solution. But here, what would happen is it would not prevent the adversary from inferring what you were doing because activities across time are correlated, right? And notice, so in differential privacy, when we had a lot of database and there were a lot of people who were correlated, there we would say, okay, fine, but this is not my secret, right? So we would say that, okay, but I have the agency. But here that is not true, right? There a single individual would have the agency and they would say, I won't participate, and that's okay, right? Here that wouldn't quite be the case, right? It's a different setting.
I apologize. I'm actually still stuck on Moshe's question. I'm having trouble understanding those.
Moshe is also stuck on Moshe's question.
Okay, so why don't we come back to this after, at the end of the talk, right? So this is, this is relatively basic. I can work out some calculations for you guys at the end of the talk, okay? So then the other option is, entry group DP, right? Here, what is happening is all the entries are correlated, right? So here again, you would add noise with standard deviation T, and that would again be too much noise. Okay. And so, so now, the question is, how can we?
An important point is that you're assuming that all the entries are correlated.
Yes, that is true. Let me finish. Let me finish this talk, Marco. Okay, so what we are hoping to exploit out of this is, it is true that all the entries are correlated, but, so then you can say, okay, so what do you expect to gain? So what you do expect to gain over here is that even though everything is technically correlated, the average amount of correlation is not that high. Right? And this is exactly what we will exploit. What we'll exploit is that, if you look at time entry 1, your correlation with time entries that are really far away is really low, right? So that is why we expect to do anything in this case, right? And that is why we expect to get a gain, and that is exactly what we will exploit. Okay. So how do we define privacy in these cases? So we are going to use pufferfish privacy, which was some very beautiful work which came out of the database community by, and this was proposed by Kiffer and Machana Vajhala in 2012. Let me talk about the definition, right? So in pufferfish, you have three, so you have, there are three parts, components to the definition. So the first is our set of secrets, right? So our set of secrets, which reflects the information that is to be protected, right? So an example would be you may want to protect Alice's age is 25 or Bob has a disease, right? So the point I want to make here is this information might be more fine-grained or more coarse-grained, right? So you may not care if I get to know that Alice's age is, Alice is like a minor or not, but I don't, so Alice doesn't want to be known, it's okay if you know that Alice is not a minor, right? However, it's not okay, but you want to maybe protect the age within a certain small range, right? So that is permissible, right? The other thing is, you may want to protect specific features, Bob has a disease or not. Okay, so that is the secret set. You also have pairs of secrets. So, here again, a pair of secret could be Alice doesn't want it to be known whether she's in her 20s or in her 40s, but maybe it's okay to know that Alice is, let's say, below retirement age. Okay, so that may be okay. Another one would be maybe, an example would be, Bob is in the data set or Bob is not in the data set. Maybe you don't want the adversary to be able to tell across this, okay? Finally, what we have is a distribution class, theta, and it is this distribution class that will be used to model the correlation in the data, okay? So here, what is happening, so how do you have this distribution? So what would be an example of this distribution class? One example would be maybe you have this connection graph G, and then you have some probability. So you can say, so maybe the disease transmits with a certain range of probabilities, and this is the connection graph, right? It'll transmit with this probability. Another one would be, so this is the kind of thing that we would be using in the physical activity monitoring example. So you have a Markov chain whose transition matrix lies in some set of transition matrices, right? So this would be another example. And this is this theta that is used to model the correlation in the data, right? So the way to kind of think about theta is theta reflects the adversary's belief about something that about the data, right? So it reflects the adversary's belief about the data, okay? And this is how you how you define pufferfish, you say that an algorithm is epsilon pufferfish private with parameters s, q, and theta if for all pairs si, sj, and q, for all theta in theta x, drawn from a distribution theta, the likelihood that a of x is equal to t conditioned on si and theta is at most e to the epsilon times the likelihood that a of x is equal to t conditioned on sj and theta, right? And the way this differs from differential privacy is, there is the presence of this theta, right? And this probability is with respect to the randomness in the algorithm as well as this theta, okay, as well as this distribution theta, okay? So
The secret pairs.
So the secret pairs are, you can just design them, you can build them into your algorithm. So, they could be Alice's age is 25 versus Alice's age is 26. So these could be secret pairs. And they would, so this is very much a meta framework and they would very much depend on your application.
I was talking about the capital S. Where do you use capital S?
So capital S is your SISJ is, so Q is a subset of S cross S.
It does not appear later anywhere else in the definition.
Yeah.
What happened to S?
The small s are in the
Yeah, so this is implicit in Q. So Q is a subset of S cross S. That's all you need to know. Yeah, so it's kind of, so I agree it doesn't appear in the definition. It's useful for introducing Q, I guess. That Q will be a subset of S cross S.
But it seems strange. You're trying to protect the secret, right? So where does the secret show up in the definition?
Over here.
s's are secret.
Yeah. So you have pairs of secrets that you don't want the adversary to be able to distinguish between. So this is kind of like, Kunal's red worlds and blue world.
Suppose I delete secrets. I delete everywhere the letter S.
Yes.
Look to me like I still get a perfectly good definition.
Yeah, this is fine, yeah. Yeah.
There is a rule in editing. If you can delete something and you don't change the meaning, delete it.
Right, okay.
Why do we have secrets at S if it does not appear
Okay, yeah, I agree with you, yes. I mean, this is the secret set S is just an artifact of making it just more understandable.
Trivial thing.
That Q is a subset of S cross S. So it's just, yeah, I agree with you, yes. The definition could be written without, yeah, I agree completely, yes. Okay, and so, if you think of Kunal's red and blue world, so think of this as the red world and think of that as the blue world, and, so that the red world is where secret I holds and blue world is where secret J holds, right? So this is kind of like that. And so, in fact, what they showed was that it generalizes differential privacy. These are looking at slightly different frameworks, but, yeah, slightly different, I would say, kind of philosophies, but anyway, so generalizes differential privacy. In fact, you can show that differential privacy is equivalent to a form of pufferfish when these things hold. So when your secrets are of the form person I has value A for all I, all A in domain X, right? And your pairs of secrets are of the pairs of the form person I has value A versus person I has value B, right? And theta is the set of all distributions where each person I is drawn independently, right? So this is, and then the other question is, what happens when theta is all possible distributions? Well, you can show that no utility is possible under that case. So this is, something that, which also agrees with what Kunal was saying earlier about, if you can make any, then there would be no utility possible, right? Any any kind of connection and these things are allowed, then there would be no utility possible. Okay, so now, we have defined this, defined pufferfish. Question is, how do we design a mechanism for this? And, there were several special case mechanisms before our work, including some, very recent work and some concurrent work with us. And the question is, can we define a completely general mechanism, which is analogous to, I guess, Kunal called it a Laplace mechanism, right? So we had the sensitivity mechanism where you look at a function, you look at its global sensitivity, and you add noise proportional to it. Question is, can we get something like that for pufferfish? And what we show is that there is something like this. So we do define an analog to sensitivity, and that is, so this is what we call the Wasserstein mechanism. Okay, So what is the what is the intuition? So in the sensitivity mechanism, what we would be doing is we would look at two data sets, D and D prime, which differ in one person's value, and we would find the worst case distance between them. Okay. In our case, we don't really have two data sets. What we have are these two distributions, right? So the probability of the function that we are trying to estimate, the distribution of the function that we are trying to estimate, conditioned on Si and theta versus the distribution that we are trying of the function conditioned on Sj and theta, right? And now so now we have these two distributions. What is really the relevant distance? Okay. And as it happens, if you write this down, you write down the definition and stare at it long enough. What happens is the relevant distance turns out to be what is called the infinity Wasserstein distance. So this is, I guess a lot of you have probably heard about the Earth mover distance. So the Earth mover would be L1 Wasserstein, and this is the infinity version of it. Okay? So what is the infinity Wasserstein distance? Suppose you are given two measures P and Q, and GPQ is the set of all joint distributions which has P and Q as marginals, right? So the infinity Wasserstein distance is going to be the infimum over gamma in this set, right? Let's say maximum x pairs x and y over the support of gamma, the distance between x and y, right? So let's say you have a metric. So what you're trying to do is you are trying to look at the best, so you're trying to look at the best coupling and the maximum distance that you move any probability mass due to that coupling. Right, and that is your infinity Wasserstein distance, right? So just to give you a pictorial representation, suppose this is your P and that is your Q, right? And you're trying to move some probability mass from P to Q, okay? And so maybe so you want to move some mass from P to Q, and you want to constrain the maximum distance moved by any probability mass to be as small as possible. Okay, and that small, that objective value is your infinity Wasserstein distance. Okay, so you move 0 from here to here. This moved by 0, right? Because it hasn't really moved any distance, right? And now you take your 1, you move it up to here. So this is 1, and you move the 1 thing over here. But you have a probability mass at k, and you have to move that too. And that, the best you can do with that is you can move it to k minus by a distance of k minus 1, right? And in this case, it will be k minus 1.
So
yes.
Don't you need to use gamma somewhere in the distance? Maybe multiply that with gamma of xy. I don't know.
So in this case. No, that's a good question. So here you don't. There are some cases where we can show that this is tight. And this is, so my intuition is that this is partly because, the differential, these kinds of definitions, you are just looking at the worst case ratio. So some cases we can show that it's tight. You're right. So if this was kind of an average case definition, you would need to weigh by gamma. But in this case, it's not always tight, but there are some cases where this is tight. So in this case, the infinity Wasserstein distance would be k minus 1. Okay? And here is the Wasserstein mechanism. You look at your function that you're trying to approximate. You have your Pufferfish framework and data. For each Si, Sj, and Q, theta and theta, you define these two, so these are essentially the distributions of the functions conditioned on Si and Sj. You calculate the infinity Wasserstein distance between them. You find the maximum of these over I, j, and theta. And then that is, an analog to your global sensitivity. And then you add noise proportional to W star. That is, W star is analog to global sensitivity. And then you add noise proportional to W star over epsilon. Okay, so that is the Wasserstein mechanism. Okay, so now, there are good properties. It's epsilon private. It reduces to sensitivity. And this also reduces to sensitivity mechanism, by the way, when you are looking at differential privacy. Okay? The problem is that computational efficiency, right? So, we have to do a lot of work, and, and the question is, can we do any better? Okay? And what I will show is for some specific cases of correlation that includes our chain example, we are actually able to do much better. Okay? So what kind of correlation across data we are looking at? Well, we will be looking at Bayesian networks. So what is a Bayesian network? So this is, these are very commonly used in machine learning. Each node is a variable, and they're all connected into a directed acyclic graph. Okay? And the joint distribution across variables is probability of x1 to xn is product over I, probability of xi conditioned on the parents of xi, right? And this is, Markov chains, and a lot of other things fall into this, and this is very commonly used in various machine learning applications. Okay? So let me start. What can we hope to exploit here? So let me start out with a simple example. Let's say we have a Markov chain where each xi could be 0 or 1, and we have these state transition probabilities. So you stay in the same state with probability 0, move to a different state with probability p, move to a different state with probability 1 minus p. Okay? Now, let's say we are trying to hide x1. If you look at what happens in x2 is actually quite correlated with x1, right? So if when x1 is 0, probability that x2 is 0 is p. When x1 is 1, that is 1 minus p. However, if you look at xi, where I is, a distance I away, then the probability that xi is 0, conditioned on x1 is 0, is half plus half times twice p minus 1 to the I minus 1, right? And if p is not 0 or 1, this is actually really quite small, right? And what this means is as you walk further and further away from x1, your influence is really diminishing with time, right? And this is kind of what we are hoping to exploit, okay? And this is what we will get, okay? So here's the main idea of our algorithm. Suppose we want to protect x1. We have some nodes that are local to x1 which have high correlation, and then we have the remaining nodes that are almost independent, right? What we are going to do is we are going to add a lot of noise that will hide the effect of the local nodes, and then we'll add a small correction term that will account for the rest, which are almost independent, okay? Okay, so I talked about almost independence. How do we define independence? As it happens that in this case, if you do some calculations, the measure of independence that becomes relevant is what we call the max influence, okay? So what is the max influence? The max influence of a node xi on a set of nodes xr is the following. This is the maximum over A and B, where xi, A and B are the values that xi can take, right? Xi takes values A versus xi takes values B. Supremum over all theta in your distribution class, maximum over little xr, probability xr takes the value little xr conditioned on xi equal to A over A and theta, over the probability that xr takes value xr conditioned on xi equal to b and theta, right? And if these two were, if xr was independent of xi, this would be 0, right? Because this ratio would be 1 and the log will take it to 0. When it's close to 0, that means it's sort of, it's close to being independent. And as it happens, if you do the calculation, the kind of correction term that we would need for this sort of thing would be of the order of, of the form of e to the this max influence. Okay, so fine. So now we know how to measure independence. But the question is, you have this, you have this graphical model. How do you find large independent sets, right? And in general, brute force search is expensive. And what we will do is we will talk about a way in which we can use some of the structural properties of the Bayesian network itself. Okay. So what is the structural property? Let me start with a basic definition that, I guess the graphical models people are familiar with. So there is this notion of what is called a Markov blanket. So what is a Markov blanket? The Markov blanket of a node xi is the set of nodes xs such that xi is independent of the rest of the graph conditioned on xs, okay? And this is, so this is the minimal set of nodes, right? So, and usually this is the, not usually, in general, this is the parents and the children and the other parents of the children, okay? So this is, it's called the Markov blanket. For our purposes, we need something a little bit different, a little bit more general. So we defined a notion of a Markov quilt, which is a more general Markov blanket. So what is a Markov quilt? XQ is a Markov quilt for xi. If you delete XQ, then that will break up the graph into xn and xr, right? And xi lies in xn, and xr is independent of xi given xq, okay? So here what is going on is xq is kind of the boundary, xn is like a neighborhood that's surrounding xi, and xr is the rest of the graph, okay? And what we want is xr is independent of xi conditioned on xq, okay? So if you, to see how this is a generalization of Markov Blanket, in Markov Blanket, is a Markov quilt where xn is simply xi, right? And now what we are doing is we are allowing a larger set of nodes xn. Right? So that is exactly how we are generalizing this. Okay, so we are allowing a larger set of neighborhood nodes, and why we need that will become clear very soon. Okay, so okay, that's all very well. How does this relate to our algorithm? Well, remember what we were hoping to do is we were hoping to have some local nodes which will have high correlation, and then have some almost independent nodes, and then we were hoping to add some correction term for them. Okay. Now, what will happen is xn will be our local nodes, given the Markov quilt, and xq union xr will be the remaining. Okay, and we don't really need to worry about xr because conditioned on xq, xr is independent, so we don't need to, when we do this, when we test for max inference, we only really need to look at xq. We don't really need to look at xr because conditioned on xq, we don't need to worry about it. Okay? And now, the question is, how do we find a good Markov quilt? Well, what we can do is we can search over Markov quilts off the graph to find one which needs the optimal amount of noise. And, we don't need to really search over all Markov quilts. If we could search over all Markov quilts, we will find the most optimal one. But if we have a set of really plausible Markov quilts, which is a smaller set, then, we could search over them, and, that would give us more computational efficiency. And, as we'll see in some cases, that is helpful. Okay? And so how do we go from these Markov quilts to the amount of noise? So as it happens, if you're using Markov quilt XQ, then the amount of noise that you need to add sort of looks like this, right? On the numerator, you have the cardinality of xn. So as xn grows larger, the amount of noise grows larger. But as xn grows larger, your xq also gets further. So its max influence goes down, and this correction factor will go down, right? So in the denominator, you have epsilon minus this max influence, which is kind of the correction factor, which will go down. Okay, and you need to balance these two effects, right? So as you get further and further, your xn gets larger, this gets smaller, and as you get closer, your xn gets smaller, but this gets larger, right? So what you need to do is you make sure you balance these two effects when you choose your Markov quilt. So then this is essentially the Markov quilt mechanism for each xi. You find the Markov quilt xq for xi with the minimum which has core si, and then you maximize over each xi because you need to protect each of these nodes. Okay. And advantage, so this will preserve epsilon pufferfish privacy. We can show that. Advantages is that it's polytime in special cases. Okay. Now coming back to our example on physical activity monitoring, remember we had this, we have this Markov chain. Here what happens is that the minimal Markov quilts are of really simple forms, right? If you're looking to protect a node xi, Markov quilts have the form xi minus a, xi plus b. The minimal Markov quilts have this really nice form. So this makes the search very easy, right? So it's efficiently searchable. So there are not that many things to search over. And in this case, as it happens, we can do even further, do more things. We can clean things up even more. So if P theta is the set of transition matrices describing each theta, then under some assumptions, essentially, various ergodicity style assumptions, the two relevant parameters are, one is pi sub theta, which is the minimum probability of x under the stationary distribution, where the minimum is over any theta in your class, and then g theta is the minimum eigengap, right? So if you have a class theta of your transition matrices, all you need to know are these two parameters. You don't need to check for every theta one by one, which can help efficiency quite a lot. And in this case, you can even write down not exactly the max influence, but an upper bound on the max influence in closed form, right? Which makes life much more simpler, okay? And so here is the algorithm. And if you run it naively, the runtime will be t cube, and with some optimizations, you can bring it down to t square, where t is the length of the chain. And obviously, this is going to be statistically consistent. And then one more thing that we can show here is that it also composes. So remember, the Kunal talked about if you use the same data set many times, then the privacy budget goes down gracefully, right? In general, in Pufferfish, that is not true. But for this particular mechanism, we can show that this is true. So this will compose. Okay, and so we can show that this is true. And I believe it's partly because we are doing, some sort of group DP over the local nodes plus a correction factor. So I think that's my intuition why it's the case. Okay, so let's look at, in the remaining 5 minutes I have, so let's maybe look at some simulations and experiments. So first we look at, a very simple 1D simulation. You have a Markov chain with, states 0 and 1, and there are these two parameters, right? So P is you go from 0 to 0, and Q is you go from 1 to 0. And we are looking at a model class theta. So theta, to describe each model, you need two numbers. And what we will do is we will say that these numbers lie in some interval. So the model class is an interval, the numbers lie in this interval. And just so that I don't have to do 3D figures, I will make the interval symmetric, right? So I'll say we are looking at intervals of the form L to 1 minus L, okay? And we are looking at sequences of length 100. And here is what we get. So Markov Quilt mechanism is our stuff, and this inferential privacy is this other concurrent work due to Ghosh and Kleinberg. And these are some results. So what you see here in the x-axis, you see L. Right, so L measures, if L is small, that means you are looking over a wider model class, and you expect this to happen. So if you are looking over a wider, trying to guarantee privacy over a lot or more adversaries, then obviously your performance will get worse. So you expect this to happen, and on the y-axis you have normalized error. So what we see, so this gray line, so this GK16, their algorithm will work only under certain conditions on the parameters of theta. Right? And the gray line is where this condition is. So to the left of the gray line, their algorithm doesn't work. To the right of the gray line, it does work. Okay? And what we see is as we get closer to L equal to 0.5, so L equal to 0.5 is when things are independent. So the states are all independent. So as we get closer to L equal to 0.5, their algorithm does better and better. And it will, very close to L equal to 0.5, it will do better than our algorithm. But our algorithm works for a broader range of parameters. And kind of in this region, between this gray line and this area, our algorithm will work better. So it's a mixed bag. If your algorithm, if your theta is really close to 0.5, then they will do better. For a broader range of parameters, our algorithm will work, and for some range of parameters, will do better.
On 0.5, you can compare also with differential privacy.
Yes, 0.5 you can also compare with entry differential privacy. Yes. So finally, this is some very preliminary experiments on real data. So this is a data set that we got from our medical school on, so they have some data on physical activity performed by an overweight subject. And what they're hoping to do is they're hoping to kind of aggregate this data, and based on the aggregate data, they may want to give recommendations to subjects and build apps and stuff like that, right? And here what we did was, again, we looked at this histogram. So there are basically four states, so walking or running, standing still, standing and then moving, and sedentary. And if you run the Markov Quilt mechanism, what we found was that the L1 error was 0.012. Group DP, obviously you can't really expect it to do very well because it's the entire Markov chain is, and there you get 0.214. And what we found was that GK16 in this case doesn't apply, because if you look at the transition matrix that you get from the Markov chain, those parameters, they actually lie on the other side of the gray line. So we found this for this data set. Similarly, here's another one. We looked at some electricity consumption of a single household in Vancouver. So we looked at the electricity consumption and then we discretized it to a whole bunch of levels, right? And this is the histogram. Again, your Markov Quilt mechanism is, giving you decent results. I think this one is for epsilon equal to 1. The previous one probably was larger epsilon. I think the previous one was epsilon equal to 5. So here, Markov Quilt mechanism is giving decent results, but GK16 also doesn't apply because, again, the theta falls on the other side of the gray line. Okay? So in conclusion, we have talked about privacy of correlated data. We have given 2 new mechanisms, looked at this Markov Quilt mechanism. We have kind of worked with it a bit more, established some composition properties. Future work is how can you get more efficient mechanisms, more detailed composition properties, maybe I think even more problems that fall in this area, and look at what kind of models are interesting for them, and so on. Okay? And finally, I will stop with thanking my co-authors. So Shuang is my student. She's the one who did a lot of work on this paper. Yizhen is also my student. And Mani is my colleague from UCLA, who's the one who proposed this problem to me in the first place. So he said, oh, we have this problem with all this data. You do privacy. Can you say something about this? Okay? So thank you very much.
Time for a couple of questions.
So it's just a very basic question. So your conclusions depend on the on the class of model you start with.
Absolutely.
For describing the correlations, right?
Exactly. So you say that if your adversary's belief lies in this model, then they can't. Yeah, that is absolutely true. Yes.
Do you know of any queries and ways to noise it up that are robust to all distributions?
Okay, so that's an excellent question. So if you have all distributions theta, then you can't guarantee any utility. However, what we can show, so we have this theta, right? What we can show is if there is a slight model mismatch, right? So adversary's belief doesn't really fall in theta, but it falls in something close to theta, then we can guarantee epsilon plus some measure of that closeness, right? And the measure is actually not KL divergence, but it's it's of the order of it's basically max, some measure of max divergence. So how in statistics we have this theorem for likelihood-based inference that if you have model mismatch, then what you are getting is something the KL divergence is the gap. Here it is max because of the nature of privacy.
So actually, I don't have a question. So your ultimate goal is to find how much noise to inject in the data.
Absolutely.
That's your ultimate goal. Now, if I don't know anything about computer science, I have data, I would say, I'm going to add a Laplace and whatever, 0.3, it's some noise. And if I think back what you're doing, you're offering actually a guarantee over the secrets and the distributions and the combination of secrets and distributions for which this noise protects against. So you might want to simplify it. So the user gives you the noise. That's how much noise I want to add. When you can tell them, okay, this is how much you're getting.
That is actually a very fascinating way of putting this. So yeah, that's a very interesting point. Yeah. Yeah, you're absolutely right. That's a very nice way of putting it. Yeah, absolutely.
Okay, so I think everybody's hungry. Stop here, and we resume at 2 o'clock.